come back to next up, where we tackle interview questions that don't really fit into the theme of variation on a theme. So we just take one specific interview question, have a deep dive on it, and then have a look at a concise 2-3 sentence answer for that question. And today we are staying in the realm of machine learning. Question comes from houseofbots.com. What is gradient descent? And the deep dive for that question is going to be coming from ML Cheat Sheet at readthedocs.io. And it starts up with like an introductory sentence. Gradient descent is an optimization algorithm to minimize some function by iteratively moving in the direction of the steepest descent, defined by the negation of the gradient. So at each point in your continuous function, you can query the local derivatives that form the gradient vector that basically always points into the steepest ascent, so in the direction where the function changes the most. And we want to go downwards because the function in question that we define on our problem is defined as a cost function or as an error function. And you want to have like the minimal cost or the minimal error, meaning the closer you get to zero, the better you fit your prediction to your data, so to say. Okay, here they motivated with a three-dimensional graph, like some sort of topological map. Our goal is to move from the mountain on the top right corner to the dark blue sea on the bottom left. So mountain bad, Mariana Trench good. The arrow represents the direction of the steepest descent, negative gradient, from any given point in the direction that decreases the cost function as quickly. Interesting thing here that we can see already, yes, if we go from this highest point leftwards into the left direction, yes, we may actually end up getting where we want to be, that deepest spot on the map. But what happens if we go slightly to the right and then following our steepest descent? We might end up getting stuck in a local minimum. So that's that we would have to keep in mind immediately. Starting at the top of the mountain, we take our first step downhill in the direction specified by the negative gradient. Next, we recalculate the negative gradient, passing the coordinates of our new point, and take another step, and so on, up until we are at the bottom of our graph, or have like our local minimum. The step size, or like how far from one point given a certain gradient we go to the next point, is called the learning rate. With a high learning rate, we can cover more ground each step. But here's the thing. So you might end up overshooting and end up oscillating. So just imagine you are here and you get the direction this way. So roughly in increasingly positive direction, and you just like overshoot to a point here. And then this point tells you you should go in the other direction again. So you overshoot, you might up ending up here, and so on and so forth. You might actually end up oscillating around your true local or global minimum. So that's like a tricky thing to just find a nice, good learning parameter. A low learning rate is more precise, but calculating the gradient is very time consuming. And here they back everything up with the actual math behind it. So key thing here is you formulate your cost function in a way that is continuous and differentiable, one-differentiable, in order to calculate your gradient. So here it's like a classical mean squared error function. And then here we get like the gradient vector for each for each coordinate with the derivative. So df/dm and df/db for m and b gives you these two derivatives that you use then to improve upon. So this basically gives you the gradient, and then you use the gradient with your learning rate in order to determine where you want to go next for a given point. And to glue this all into code, you basically do that thing here. So that's what you need to do, like calculate the partial derivatives of all, and then use this as an update on your new position and then return your new position from that. And that's all the magic to it. But the key lessons there is, yes, you go to a minimum. Yeah, you inevitably end up going to a minimum. That minimum might not be the global minimum, it might be the local minimum. And if your learning rate is set too high, you might end up oscillating infinitely around a minimum by just continuously overshooting between the, say, left and right part, like frontal and like front and backward part of your direction in which you are going. So with that in mind, let's go back to the answer to that. Short answer, like in simple words, today comes from medium.com, and the user Monjoli presented the solution for that. In simple words, gradient descent finds the parameters that minimize the cost function error in prediction. Gradient descent does this by iteratively moving toward a set of parameter values that minimize the function, taking steps in the opposite direction of the gradient. And again, I think this is something we should stress here. Calculating the gradient gives you the direction of the steepest ascent, where you go highest. But if you define your function in a way that it is an error or loss function, you search for 0, you search for the smallest value. So therefore you have to go in the negative direction. So gradient descent follows the opposite or negative direction of the gradient. And basically, if you just come up with those 2 sentences as a description for gradient descent, you make a good introduction on your knowledge for gradient descent and for answering the question that you've been given.